Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine needing to build a perfectly symmetrical, incredibly stable container, using thousands of identical pieces, all without a blueprint or external energy source. That container needs to survive harsh chemical environments and explode open at the precise moment it needs to infect a cell. This is the daily reality of every virus on Earth, and they solve this immense engineering challenge using math so advanced, it breaks the rules of high school geometry. They exploit the principles of hyperbolic space. Viruses are essentially biological capsules of genetic material. Their protective shell, the capsid, must be stable enough to survive in the environment and symmetrical enough to assemble quickly and spontaneously. For decades, virologists noticed a recurring theme. Most viruses, from the common cold to the devastating poliovirus, adopt an icosahedral shape, a structure with 20 triangular faces. In standard Euclidean geometry, the world we perceive, a sphere is the most efficient shape to enclose volume. But building a sphere using identical protein units is impossible. You must introduce curvature. The solution, first mathematically formalized by Casper and Klug in 1962, uses the geometry of the truncated icosahedron, which involves combining 5-sided units, pentamers, with 6-sided units, hexamers. Think of it like tiling a flat floor. A flat surface can only be tiled perfectly with shapes whose internal angles add up to 360 degrees, like squares or hexagons. To curve that flat tile pattern inward, to create a sphere, you must introduce defects. Places where the local geometry is slightly tighter, like a pentagon in a field of hexagons. This creates positive curvature. Now, here is where the concept gets truly mind-bending. The local structure of the viral capsid, particularly in giant viruses or bacteriophages that require specialized non-spherical shapes, often relies on principles closer to hyperbolic geometry. Hyperbolic geometry, or non-Euclidean geometry, is the geometry of negative curvature. It looks like a saddle or a frilly lettuce leaf. In hyperbolic space, the interior angles of a triangle always sum to less than 180 degrees, and you can tile a space where 7 or more identical shapes meet at a single vertex. If you tried to tile a flat floor with 7 squares meeting at every corner, the tiles would immediately buckle outward, forming a complex, infinitely branching surface. Why does a virus, which ultimately forms a finite, closed structure, rely on the rules of infinite, negative curvature? The answer lies in self-assembly and frustration. Viral proteins are designed to prefer local interactions that mandate negative curvature. Imagine the protein subunit is programmed to think it should tile a hyperbolic plane. When thousands of these units snap together, the overall frustration caused by trying to fit a negatively curved structure into a positively curved, finite spherical boundary dictates the precise assembly pathway. The structure is forced to introduce specific defects and folds to resolve this fundamental geometric conflict. In essence, the proteins are not following a global blueprint. They are following local geometric instructions that are inherently hyperbolic. The final structure is a compromise between the protein's local desire for negative curvature and the requirement to close into a sphere, which necessitates positive curvature. The controlled balance of positive and negative curvature is what allows viruses to achieve the immense stability and size diversity observed in nature. This isn't just biological curiosity. Scientists are now using these geometric insights to design synthetic molecular cages, nanocages and drug delivery systems that possess the same robust, self-assembling properties as viruses. By programming synthetic materials to follow the geometric rules of hyperbolic tiling, researchers can create stable, complex containers efficiently, opening up new frontiers in medicine and material science. The humble virus, in its silent, deadly efficiency, is teaching us how to build at the atomic scale, proving that sometimes the most sophisticated engineering happens when you bend the rules of reality itself. For more incredible facts like this, don't forget to subscribe and turn on notifications.